Hi everyone, this is a tutorial for Microscopy Nodes 3.1 in Blender 5.2 or newer. We are going to learn how to load and visualize microscopy data in Blender. That can be fluorescence microscopy, electron microscopy, or any other kind of microscopy data that produces a voxelized image. We will also look at data with multiple channels and data with a time axis. The important thing is that the loading workflow is essentially the same for all of these datasets. What changes is how we choose to represent and visualize the data after it has been loaded. We'll start with a multi-channel fluorescence dataset because this kind of encompasses a lot of the basic features, and then I'll show how the same controls can be used for dense FIB-SEM data and for a time series dataset. So here we are in Blender, and we can click away the splash screen. And first we would need to install Microscopy Nodes. We can find that under Edit and then Preferences and find Get Extensions, and here we can search for Microscopy Nodes and press Install if you have not yet installed it. And once it's installed, it should show up in here with a check mark, and here you can also find extra settings. We can click this away and go back to our scene and load our data. Before loading, I first want to delete everything in the scene, which we can do by selecting everything with A and then pressing X to delete everything. The Microscopy Nodes panel is in the scene properties, and this is where we can put in a dataset to load. We will start with an expansion microscopy dataset of an RPE1 cell. This is an online OME-Zarr dataset, and I've put the address in the description. We can copy this address and paste it into the dataset field. If you have a local TIFF or another local dataset, you can instead press the folder icon and select it from your computer. Once the address or file has been entered, Microscopy Nodes will populate the metadata. We can now see more information about the dataset and choose how it should be loaded. We can start reading these settings from top to bottom. The first important choice is the scale or resolution level that we want to load. Blender is generally more responsive when we work with a smaller version of the data. So OME-Zarr datasets can contain several multiscale levels, so Microscopy Nodes let us choose between them. For a large TIFF file, Microscopy Nodes can also create downsampled versions automatically on the fly, which gives you the same kind of selection thing. It is usually best to begin with a small scale while building the scene, and once the visualization and camera and animation are ready, we can reload the data at higher resolution for the final image or video. For this tutorial, I will choose the scale S3, which is around 50 megabytes. The scale of the data also matters because a local file will be written of this scale, which will be usually written in the temporary files, but if you want to work on a project for longer, you can also set it here with a local specific path or with the project. And then the last thing that we can set is how to load all of our channels. This dataset has 4 channels. For every channel we can change its name. We can choose how it is loaded and select an initial color and decide how it should be represented. A channel can be loaded as a volume, which preserves the full 3D intensity data. We can load it as a surface, where a mesh is extracted at a chosen intensity threshold. Or we can load it as a label mask, which is useful for segmentations, which means that your data already needs to be structured as a segmentation. We can also choose whether a volume starts as emissive or scattering, where emissive it means that the volume emits light in the scene, which is very common for sparse fluorescent data, and we can turn it to scattering, which is better for dense data, which means that the data will reflect light from the Blender scene. And then we can pick the color, or we can pick a nonlinear color map. For now, I will just keep all the default settings and press load to get the data into Blender. So we have loaded our data, and we can see in our scene collection we have the dataset and a hierarchy of objects that were created by Microscopy Nodes, which is the dataset named after our file, a volume, a slice cube, and the axes. In the actual scene, we only currently see a box with a blob inside, because our render mode currently is not set in a way which we can see the data. By default, it opens in the solid rendering mode, which is designed mainly for meshes. So to see the microscopy volume, we need to switch either to Material Preview or the rendered preview. And these will have slightly different features because they use a different render engine in the background. The material preview normally uses Eevee and is useful for fast interaction. And the render preview uses cycles, which is slower but supports more accurate ray traced rendering. Which one works best also depends on your computer, the data, and the kind of visualization you're making. So I would switch in between these two depending on your things, and you may even want to change the render engine of Blender to Eevee as well if this is just much better for your data. But now we can actually see the data set, and we can go back to our scene properties and also match that our blue is indeed our NHS ester. In orange we see the nucleus, in red we see the tubulin, and we see the acetylated tubulin is over here as the centrioles, but they are hard to see. As in any microscopy software, we need to be able to adjust the brightness, contrast, opacity, and color of each channel. In Blender, these settings are part of the material shader. We can find the shader by selecting the volume and then going to, in the top bar, selecting the shading tab. This will then open a different view where we can set again our correct render mode that we want to work in. And below here we have the nodes interface. This nodes interface consists of multiple branches that are added together for each channel. For now I will focus on the AB tubulin channel because I think it is the nicest one to quickly show what the capacities are. To make this slightly more visible, I'm going to go into, with the volume selected, we'll go into the wrench icon and turn off the other channels so we just see the tubulin. Now, how this shader works is that here the data is loaded, which then goes through two boxes defining the limits. Here's a histogram, and here is a left limit and a right limit for the color on the top and for the alpha, which is the opacity, on the bottom. So we can change the minimum value of the data to be included to be opaque by changing this minimum value in the alpha. Currently, the color limits don't do anything because we only have a single color set. Because this is effectively, we can read this left to right and follow the lines. The color limits go through this color map and then go into the shader. And the transparency goes into this transparency map and then go into the shader. If we want to set a different color map here, we can either do a plus here and change the individual colors. But what is easier is we can select it and right click on it, and then we can find replace lookup table, and we can find a selection menu with hundreds of different color maps from black to single color, but also things like viridis or plasma, which are common scientific color maps. And then we can see that if we put plasma here, that currently we don't really see the top of our range much. So we can start moving specifically our color contrast limits to encompass this. Additionally, outside of just the range of alpha, where for the min and max, we also have a block to change how the alpha is being interpreted. Here this contains a multiplier, which is how intensely every voxel will contribute to the final render. So in an emissive render mode, this means how much light does it give. In a scattering render mode, it means how dense is the fog at that pixel, so how much does it stop light. And there is a switch between a linear alpha, where things at 0 will be very transparent, and things at 1 will be most opaque, and a constant alpha, where everything that is inside the limits will have the exact same transparency, and we just see a strict mapping of our color map. For emissive data, it's often best to take these linear alphas and just crank up the multiplier a bit to find a nice setting. However, this is different if we have a scattering render mode. We can switch between emission and scattering either with the light bulb change when we're loading, or here by switching this slider from 0 to 1. However, when we're doing in full scattering, currently we do not see anything because there is no light set in the scene. And this is because the background color is black, and we can change this to white to show the data. And then we can see that we find a complete scattered dataset. This looks best in cycles because this can actually show all the scattering between different regions of the dataset. However, cycles with scattering data can take a long time to render, and for this we can see up here that right now it's at 6 out of 1024 samples it will take before it considers itself done rendering. You can decrease that maximum if you need to, if you go to the render settings of Blender. But if we wait a while for the render, we can start to see that we see really pretty the density of our microtubule network show up in our scattered sample. So sometimes it may also be very good to do scattering with fluorescence data, and other times it might be good to do emissive with EM data. But right now just turn back to emissive and make the background black again, showing a linear alpha with a wider color contrast range. We do not always need to edit everything directly in the shader. We can also return to the Microscopy Nodes loading panel and reload our dataset. As long as this reloaded field is pointing to the right object, we can just change our settings in here or reload our settings in here, and this will just apply. However, this will keep our different contrast limits that we've set. This also allows us to now first build our visualization and then later change our resolution to a higher scale. If we don't want to update our settings but only our data, we can turn off this icon and we will only load a different scale. Alternatively, if you don't want to update the data and only the settings, you can use this. You can only turn on this. We can also load only specific regions at a higher scale, but for this I have a separate video for working with large data with microscopy nodes. Another thing that we can do from here is select different modes that we're loading our data. So for example, for our acetylated tubulin, we can also load this as a surface. At first this mostly looks like a large noisy cloud, which is this new surface object, and that is because currently the threshold that Microscopy Nodes applies is not completely correct, because it doesn't really understand that our centrioles are only two individual small spots, but we can, in the surface, in the wrench icon, modifiers, we can start to change our thresholding, and we can start to see here that our two centrioles can be selected, and we can now have this combined render where we have the volume but also surfaces together in the same space. And then one last thing on visualization is our slice cube, which we can move, which is it is a box that is linked to our data that we can move and rotate and scale however we want to slice our data. I have a separate video that shows all the things that you can do with slicing. For now, I will kind of keep it to this in this video, because we can also not just slice with a box, but with any mesh of a different shape. At this point, we've completed the general workflow. We've selected a dataset, we've chosen a scale, we've configured the channels, we've loaded them, and adjusted how they are visualized. So this is the basics of microscopy nodes, and anything else will just depend on your data and the exact things of your visualization, and is essentially more advanced. So I want to quickly show two other types of data to see how we handle them. So I'll both do a FIB-SEM dinoflagellate image, and I will do a video with a time axis. For loading the FIB-SEM data, I'm going to press on the holder here and say delete hierarchy to delete our RPE1 cell. Next, I will paste in the address for our FIB-SEM dyno. So our dyno flagellate has a lot of channels, most of which are just segmentation channels. For now, I want to just turn all of them off except the data, which is the original data, and the chromosomes, which will load as a label mask. And we'll load this at the S2 size. And I'm going to immediately set the color map for the label mask to a categorical color map so we can see our different individual chromosomes. And I'm going to press load. And now that I've loaded it, I realized that I wanted to turn off the light bulbs because we wanted to have this, because it is dense data and it is easier to look at this in scattering. So I'm quickly going to reload, which won't remake the files, but it will just apply these settings. We can see that we now have a blue EM dataset, which we can also make white. And we also have a label mask that lives inside of this dataset. To show the inside of this scattering render, I will grab the slice cube. So I can move it either with these widgets or I can press G to move. And I'll slice such that we can kind of start to see the label masks and switch to the shading tab. And here we can see that we're also in cycles, so we can see actually how it's really going to be visualized. And here we start to see why I really like EM data in FIB-SEM data in Blender, is because we can see cavities like this way nicer in something like Blender than we would see it in than in a lot of other software, because we can actually do a full scattering ray traced render. But for first, just to show how to make a normal EM render, I will show that you can just take the alpha limit such that it's just a completely dense block, and for example set the color to black to white. And then if we set it to black to white, we can set our range of color, and then we can just get a normal sliced version of effectively of an EM block. If we would want to create a more bright version of this, we can actually change the strength of the background color to be even brighter or add more lights. However, I think this is not the most exciting way to use Blender. I think the more exciting thing is to adapt which regions of the data we're actually showing. So we're going to create these transparent regions at all the parts of the dataset we do not want to see. Now quickly turn off the visibility of the label mask. And move our range of our alpha such that we only see the internals. We can only see the membranes. This lets us see large pockets and cavities in the volume, including the nuclei of the cell. So the controls are much the same as we use for fluorescence. However, the useful settings are very different because our data is much more dense, and we kind of need to clip away a lot of the data to show the 3D-ness of our data. And we can also see that if we turn on the label mask, that we will see that our chromosomes are exactly in the pockets of our nuclei here. This can also look good in a nonlinear color map. However, all of this will take a lot longer to work with because we need to actually calculate all the scattering of our light rays for each single frame. And this is a little bit harder, but it can make for beautiful images. Okay, so this is a quick showing of how to load a complicated FIB-SEM dataset. I will also, just to show a little bit of other interaction, I will load a time series dataset. So I will delete the FIB-SEM hierarchy and put in a new Zarr address for our meiotic nucleus. So this is a much smaller dataset, and this is again fluorescence microscopy, so we can just open this with the light bulbs turned on. And here we can see that we have synaptonemal complex, which holds the homologous chromosomes together, and the crossover marker COSA1 in C. elegans meiosis. And we can see that if we go right and left with our arrow keys, we see that the data changes. However, that is more clear when we go to layout and we go to our favorite render mode, and we scroll this up. I will put this a bit above my head. You can see that it really moves when we change the timeline in Blender. However, we also see that this kind of ends after frame 33 because this video is 33 frames long. With time data, it is often that you actually don't want to have only 33 frames for your camera movement because it makes your camera movement really jagged, or maybe you want to have some time to actually rotate around a single frame. So for this we can actually change the animation of our time axis. For that we can select our main object. So this is the holder object, and this has in interwrench icon a value called frame. This is actually the frame that's currently being read out. And here we can see how this is animated. We have a keyframe, so a specific frame where a specific value is set at frame 0, where frame is 0. And we have a keyframe at frame 33, where this frame is 33. So we can move or scale or grab these similarly to other objects in our scene with the hotkeys G for grabbing and moving. Then we have created a delay beforehand, or we can scale it with S, and then we scale it through time, and we essentially slow down our video. Then what we can also do if we want to have a pause in between is we can set a new keyframe. For example, here the frame being read out is 14 at frame 49, and we can say I, and this will set that at this specific frame 14 should be playing. If we then move this through time to frame 70, and we again set frame 14, we can hover and press I again, and then we see that we have frame 14 this whole region, and then the animation continues and is before that correct. So this is how to create a pause in our time axis. So let's summarize what we've learned. We can load our data from a local file or a distant Zarr. By putting this in here, we can select a scale. This is very small, so there's only one. We can change our metadata. We can change how we're going to load things, and then how it's visualized in the shader. Then we can slice, we can change our time axis, and we can do scattering or emissive renders. So figure out how you want your data to look at the end, and please follow along with the example data sets I have and figure out how to handle your own data. And I hope you make very pretty renders. I will have some other videos out both on Blender UI that is already out. That's a slightly older video from Microscopy Nodes, but all the Blender UI is still completely relevant. And for creating videos and images, there's also already a video out. And then I will still be releasing videos in this series about recoloring specific regions in your data, how to work with large data where you only want to reload a very small piece, different scale annotation and time annotation, and I will have a video on projecting your volume data onto a mesh. But here we've seen mostly the basic workflow for loading microscopy data with Microscopy Nodes 3.1. And I hope that you have learned for this, and thanks for watching, and I hope to see you in the next video.